Okay. Welcome everyone to our new week's seminar. So today we are going to have here Leonid Ryvkin, who will tell us about Tepui fibrations and singular search theorem.
Okay, thank you very much for the opportunity to speak. So what I'm going to report on is recent work with Alfonso Garmendia and David Miyamoto. And basically, what we wanted to do is study a certain type of singular space which appears in differential geometry. And it's a space which is a fibration. So it lies over some smooth manifold M. And it has regular fibers, but they might be kind of attached to each other in a way that jumps dimension. And more precisely, this is something which you encounter very often when you have a group action, which is fiber preserving, and it's a Lie group action or a Lie algebra action. And then at some point, the generators of the action, well, you vary the points of the base manifold, become collinear. So the things you are identifying become less. So you have individual fibers or families of fibers which are of a higher dimension. So the prototype case is you imagine R2, and you are acting by the vertical vector field dy, but you're giving it a coefficient x. So the orbits are like this. So if you take quotient, it will look like this. The reason I care about those spaces is that they naturally appear in the context of singular foliations, but in a slightly I don't know, surprising way maybe. So reason why I care. Oh. So singular foliations, there are more definitions of them around than mathematicians. I'm going to follow more or less the one of Leonid and Skandalis, which they introduced for some analytic reasons to build holonomy groupoids and be able to construct C-star algebras of singular foliations. And what they noticed is they need not just the information of which points lie in the same leaves, but also some information about the way how you are approaching the singularities. So their definition is not purely, I don't know, geometric or like on the level of the space. It has some dynamic components and it manifests itself like this. So singular foliation on a smooth manifold M is a subspace of the vector fields, which is closed under multiplication by smooth functions. And in order to have nice leaves, you kind of want, if two directions, two vector fields are in it, their commutator to be in it, so also a leaf. And then, because we are working with smooth spaces and not with analytic ones or holomorphic ones, we have to impose a condition of locally finite generation, because otherwise one can construct weird examples where the leaves are not really smooth manifolds and certain behaviors appear. So locally finite generation. I'll make this a little bit more precise later. There is also one other condition one could impose, which is something like, I don't know, maybe we don't want all vector fields and all vector fields of compact support to be interpreted as two different objects. So one simple way to solve this is we're just looking at vector fields with compact supports, they contain the same information. We will do a slightly different solution to this later, but that's one option to do. Okay, so from such a foliation, you get something which is more or less a distribution just by evaluating all the vector fields at all points. So you can do here, which is just x of m for m in the manifold and x in the foliation.
Can you break the chalk? It will be better.
Okay. Oh yeah, much better. This will be a subbundle of the tangent bundle. And of course, if your foliation is singular, we haven't assumed any regularity on the module. This will not be quite a subbundle, it will be a singular subbundle. So some fibers are of a lower dimension. And of course, one could already start looking at this singular subbundle of the tangent bundle as an object like this. But this is actually not the way we're going to do it, because this thing loses information. So if you take the foliation, let's say M is equal to R2, and we are taking all vector fields in R2, which vanish in the origin. This is a foliation. I will describe it slightly differently because we need the notation later. It's also the same thing as you just take any vector field and multiply it by a function vanishing the origin. So it's I0 x of n, and I0 is the ideal of all function vanishing in the origin. Okay, so this is one foliation on R2. And now I'm going to write down the second one. It's I0 squared of xn. So you take a vector field and multiply it with one function vanishing in the origin and then another one. Then you are allowed to take finite sums. This just describes the vector field such that x of 0 is 0, and also its differential is 0. I'm going to think out for long as the talk. Do I have to re-break it regularly? Okay. So those two are different dynamically. You can kind of, as infinity modules, they are not isomorphic. If you want to write down a minimal set of generators, here it will be 4, and here it will be 6. So here it's kind of xi dxj, so x dx, y dx, x dy, y dy. And here it's the generator of degree 2 polynomials, so x squared dx, xy dx, y squared dx, and the same with dy. So they are really different. And this thing doesn't remember everything. And so what we are going to do is, in the very end, going to bring us back here, and it will give us a sort of singular version of a vector bundle with the property that a foliation is just its set of sections. So because those things are somehow, one can already see it, at 0 something different happens than in the other points. It will not be an ordinary vector bundle. It will have jumping fiber dimensions, and this framework I'm going to describe is one means to make it precise. Okay, so the plan of the talk is written here. This was the motivation. I'm going to use diffeology as a means to talk about singularities in smooth spaces. Then I'm going to define those singular fibrations, which are Tepui fibrations. And then I'm going to report on a singular size-1 theorem, which basically tells us a certain class of module can be realized by these Tepui fibrations. Singular foliations are this type of module. Hence, we have found the 8. And then at the very end, if I have time, I would like to show a few examples that weird things are happening. So basically, the here big dragons, those are the strange things which one might not expect, which are happening in this singular context.
Can I ask a very silly question?
Yes.
Tepui, is it a Japanese name? French?
It is a name of mountain ranges in Venezuela, which are kind of those huge mountains which have sudden cliffs where they drop off.
But it's not a person's name.
No.
Oh.
So we made up the word.
Okay.
We had an internal competition among the co-authors and got some external feedback, which threw away our first 5 suggestions. And then we picked that because somehow the way how we have the big space collapsing into the smaller one reminded of that. that was the only thing which made me consider doing a slide talk, because they look really, really nice. So in case you don't have association with them, looking at them and then reading about them on Wikipedia, it's super interesting. Good. Back to math. So So roughly speaking, a diffeological space is a set with additional information. And the additional information is what are the smooth maps from Rn into it for all the n. So characterizing smoothness by how Rn's map maybe it's going to make more precise definition. And theology. On the side. X is for all n, for all u open in Rn, a collection. Maybe I'll call it dx, dux in just the maps from u to x. And so the idea is that the maps from u to x, which are in this gx, those are the ones we would like to think of as smooth. So for a smooth manifold, you think of as charts as kind of giving you local diffeomorphisms. We are kind of weakening this idea a little bit. We're just saying what are the smooth maps into our space. And for this to be a reasonable notion of smoothness, it should satisfy some properties. The first one is constant maps should be smooth. The second one is if we take two of such U's and have a smooth map between them and compose with an element here, the result should be again a smooth map. So for all f from U to V smooth. And now the idea is this is in sum Rn1, this is in sum Rn2. Now we have to compose. So dx of V, I map from V into X. And now I first map from U into V, and then do that. That should be in GXU. And the third condition is if something is smooth locally, it should be smooth globally. We want smoothness to be a local notion. So if U is the union of some I and which is now a map from U to X, satisfies that P restricted to UI is in GXUI for all I, then P in exactly, it's a concrete sheaf on the category of Euclidean spaces, meaning open subsets of Rn. So yeah, that's a so this is giving you concreteness. This is the pre-sheaf condition, and this is the sheaf condition. So examples of topological spaces are all smooth manifolds, just by the usual smooth maps. Any subset of the diffeological space is naturally diffeological. You just say the maps or the things are smooth, which, if you look in the bigger space, are smooth. Then coordinates in a slightly more subtle way. So because imagine we have some set X, we have some equivalence relation on it, we have X modulo the equivalence relation. In order to get a reasonable notion, we cannot just say the map from U to the person which lives up, but we have to take those which locally live up. So locally. So the way one should think of the topological spaces, it's a notion which retains a lot of information. So basically, you know everything about the manifold if you know its topological structure. You can reconstruct the full smooth manifold structure. You know everything about a Frechet space or a Frechet manifold, even just from its topological structure. So it recovers a lot of information. However, it is a really wild and bad category in the sense that if you have a topological space, you probably cannot prove almost any theorems about it. It's a little bit like topological spaces. If you want to have some strong, interesting geometry with which you can really work, you need to impose additional properties. Maybe a few examples of kind of slightly odd things happening. So you have the CK diffeology. So you could define, again, you take the smooth manifold, but you say that dx of u are the CK maps. So this is a well-defined diffeology. It satisfies all those properties. But of course, this is not something where you will have, for example, decent Cartan calculus. If you take the bracket to CK things, it will be just CK minus 1 and so on. And of course, you could also take C0, and you could start with X. So X is now a manifold, but you could also just start with a topological space, and it naturally carries a diffeology given by the continuous maps. Yes, maybe another example to just keep in mind. R mod Q is the diffeological group. It's a portion of the diffeological space. All maps are diffeological, so kind of those phenomena also. Now, a diffeological space.
Also, can you take one where it takes all the maps to be smooth?
Yes, absolutely. It would correspond to discrete or indiscrete topology. Choose one. Okay, so on diffeological space, you have a well-defined notion of locality in the sense that there is a natural topology associated to it. You just take those spaces and want pre-images of a set to be open. So maybe I should say what their name is. They're called plots. Originating from the French plaques, which is a little bit like charts parameterization. So, topology. We define it by plots. So you maybe a different word. O in open defined as for all plots P the image of all. Uh, For the moment we have a topology, you can talk about locality in the domain. So of course you can define topologically smooth maps. Those will be the maps satisfying exactly this type of domain. So f of x to y smooth. Those are now topological spaces. Is defined as if you take a map into X and compose it with F, it will be a smooth map in one. So for all you, I'm not writing the letter anymore. And given the fact that we have a topology, we can also talk about germs of maps. I will use the notation like this. So f of x into y, the germ of a map near little. So we just meaning that I'm allowing myself to restrict the domain to an arbitrarily small open neighborhood. It will be a little bit convenient in the sequel for doing certain definitions.
Sorry, I was saying that any such thing is called a germ?
This is a notation for a germ. So when I want to say that I'm only interested in what the map does near a point, I'm adding the point in the. It's a little bit abusive, but we'll see in a second on why. We have objects and maps, and we have the induced topology. One little warning is that if you take a subspace and then the topology of the subspace topology, it will not be the same as the subspace topology of the original space in general. This is an actually no, just Q would be an example of that. Topology of sub with the set topology not equal subspace topology. The subspace topology means only constant maps are smooth. Hence, its topology will be the discrete or indiscrete one. I'm always mixing up the words, and correspondingly, the subspace topology of Q it's totally disconnected, but it's not the discrete one. Okay. To wrap up the topology section, we will need the right notion of subjectivity for topological spaces. And there are multiple competing notions. So some of them have a categorical justification. So there is something which is like, I don't know, the regular epimorphism. So this is something which is called subduction. There is something which is called submersion, which satisfies a certain lifting property. And there is something called plotwise submersion. That's the one we are going to use. And unfortunately, they are all highly non-equivalent, and one can find very easy examples satisfying one, but not the other. So, definition. F from X to Y, plotwise submersion. And only S. For all plots from U to Y. for all little x in the U fiber of in the so the plot is called P. So I'll U to y P and take P into y and take that minus one of that. So in the fiber of the target, there exists a lift. Okay, so this is why we needed the German notation, because I really want to be able to choose any point in the lift. So there exists a lift through little x. If I don't put the condition that I just want to have any lift, I would get the notion of just subduct, a notion which would be called subduction, and it's weaker. Okay. So for smooth manifolds, this is just usual submersions, but because in principle the diffeological space X could be relatively big, just requiring that you can lift any map would be more than just requiring that you can lift maps coming from a Euclidean space. Example for smooth manifolds. Manifolds. These maybe just one sketch example of something where this clockwise condition would play a role. It's, for example, if you take over R, the fibration, so the map from X to Y is a projection down from a space which is those two lines to this line, and here you have something which behaves like X to the power of 3. And then if you come from any open interval containing the origin, you can always lift up here, but you cannot always lift through this point. So it is something which would be called subduction. In the context of diffeology, it's the weaker notion of subjectivity, but it doesn't satisfy this plotwise submerging property. Just one remark. This example is the reason why Lie groupoids are not the same thing as groupoids in manifolds. So from the groupoid axioms, you would just get the fact that you can lift things near the origin, but if you have disconnected fibers, actually, this is something Christian Bloman showed me, that you can build examples of groupoids and manifolds which are not Lie groupoids.
Can you explain the example like the so you have two spaces, one of them is this line and the other one is
yeah. So this would be y. Those two together would be x. Okay, and this is the plot u. And you just take the identity of a small interval into the neighborhood of this point, and you cannot lift through this point, but you can in total you can always lift somewhere here.
You can't lift to the middle or the bottom curve.
Yeah,
because
exactly.
The lift would look like cube root. Or
Yeah, exactly.
Something on the base.
Yes. So David pointed out to me that I could take as an alternative the map from R2 to R, which is x comma y goes to xy. It has the same property and it's a connected space, so maybe it's a little bit more intuitive. You cannot lift all things through the origin. Okay, so now this was the philological background. Now we can define proof hypothesis. So everything is happening in the category of topological spaces, but as indicated from the very beginning, I would like the base of the fibration just to be a smooth measure. Then, in order to call it fibration, it should kind of be the analog of a submersion in the context of manifolds. So I would like the map Q to be surjected plotwise. Now I would like to mimic exactly the singularity behavior that the space is locally a quotient of something Euclidean. So the way is as follows. So yeah, for all points in X, there is a plot to X through that point, such that, and then you give it the P, such that P is again a local subvector, plotwise subvector. That would be kind of just something which appeared in articles of Jakobs and Ryvkin and Marcos Ambon as generated by local subactions, that it's kind of a quotient of Euclidean spaces. But I want to have things which are kind of, the fibers are smooth and it's somehow a smooth family of smooth spaces. So I want to have such a plot, which I think of as char, which in this concrete fiber I'm talking about is injected. So injected over the fiber.
Sorry, in the previous axiom, like the notation is not like the German notation, right? Like you're not.
This is the German notation.
That's the German notation.
Well, I mean, because like German just means there is some little open neighborhood, it doesn't really make a difference. So you can think both ways, whichever you prefer.
Okay.
Okay.
So is the requirement of plotwise submersion is on the chart B?
Yes. So you want to be able to, you have some smooth maps into X.
Yeah.
And kind of you have some chart like from a manifold or Euclidean space, and you can kind of locally lift it into U from any point of view.
Is this like a local trivialization?
Yes, so it's kind of, it trivializes the fiber and extends to the neighboring fibers as a parameterization. It stops being injected in the neighboring fibers, but it still parameterizes the space.
Okay.
And so those are the relevant X terms. And then there are two technical ones which we add in order to just not have to add in brackets non-Hausdorff or non-second countable everywhere. So we will require X to be second countable. Are compact, and we do require the fibers Hausdorff. So this is really just to have proper smooth manifolds as fibers and not non-Hausdorff on non-second countable.
Now, we will be used by the Euclid.
Yes. So I would like to give first a weird example, and then for the rest of the talk, we're going to talk about the nicer class of examples. So, okay. Example 0 is fibrations of smooth manifolds, submersions. So, of smooth manifolds. Examples. The second example, I will basically, typically when I want to construct such things, I will just start with the U and tell you what the equivalence relation is. And once you kind of, that will always contain all the information. So what we'll take is, we take R2 and we put some quotient on it, and all of it will be a fibration over R, very similar to the picture in the very beginning. With an equivalence relation, and the equivalence relation will be xy will be equivalent, and not just in the the first coordinate, but in the second coordinate. So if I go to this, I will just get a cylinder, but I'm going to do this. So when x gets smaller, the diameter of the cylinder gets smaller and smaller and smaller. I'm getting something which is a little bit like a double cone. However, at 0, the equivalence relation collapses. So I'm having something like this, where one has one fiber R and a double cone. So this is kind of a little bit of a strange space, and one should think of this line as wrapped infinitely tightly around that point. So this point, it's very close to this point. The line is kind of, you know, if this, it looks a little bit like a Diablo, so this is really kind of the line, the string is completely curled up around the double. So this is not an esoteric example. If you try to integrate Lie algebroids to Lie groupoids, there are two obstructions, according to the theory. There's the theory of Kreinig and Fernandez about integration. One of the obstructions is for fiber-wise singularities, and one obstruction is for singularities when you move from one fiber to the other. And the type of singularities you can get when you move from one fiber to the other is exactly this type of singularity. So kind of this is work in progress. What we would hope to have is integrate Lie algebroids to Tepui fibration if one of the obstructions vanishes, but the other not necessarily. There is, I think there are people working on quasi-fold and Lie groupoids, so I think there are many different perspectives you can take on this, but this would be one. Okay. So now we'll switch to nicer objects. Basically, we are now going to define the vector bundles in this singular world. And okay, if you like abstract nonsense speak, a VB Tepui, vector bundle Tepui, is a vector space object in the category of Tepui fibrations over a fixed manifold. If you don't like it, it's just a bunch of data. So definition VB Tepui. V over X, V over M. The Tepui fibration plus with additionally the structure maps you would expect for a vector bundle. So 0, a map from M to V, multiplication, a map from R V to V, and plus a map which allows to add things if they lie in the same fiber, satisfying the usual vector bundle access. Or vector space access. Okay. So example. We take some smooth manifold M. We take usual vector bundles into F over there. And we just take F modulo the image of our fibrations. And that will be the Tepui fibration. And this is actually kind of one way to obtain this example we had in the very beginning. You just take R2, you take the map which maps, I don't know, generator to X times generator, and the quotient will be the one we discussed. So. And maybe we'll just do the sketch. So this is the projection. The reason why I redo the sketch is to say that you should think of this whole line to be attached to those 2 points. So I don't know, maybe I should paint it somehow differently, because this as a diffeological space is very, very different from the space, I don't know, xy equal to 0 in R2. So this would be the subspace diffeology, and this is the quotient diffeology, and this one is Hausdorff, but as a singular space, actually, yeah, very different to work with than this one. We started more or less exactly at 2, right?
Mm-hmm.
So
We'll be a couple of minutes after.
So I should also stop not far from and plus 1. So two properties which will be quite which are quite useful is that a pullback of the Tepui fibration is a Tepui fibration. So if you have n going to m and you have x over the Tepui, then f star x over n will be Tepui again. And the second one is that if you have x to m and y to n, then x times y over m times n will be Tepui 2. This is less spectacular, but those two together mean fiber products of Tepui fibrations over the same space are again Tepui. So for instance, this space here was more than the theological map, it was even a Tepui fibration itself. So it's kind of a nice notion which is preserved by some construction. Now, for source one, it's probably good if I quickly recall the classical source one theory, right? Okay, so this is one of the words. So M is smooth manifold. For a second, I'll assume connector. And I can consider vector bundles over M. And I can consider modules over C infinity one. And there is a natural map from the former to the latter, which sends a vector bundle to its space of segments, which can be multiplied as functions and added as C infinity n. The result of this will always be projective. One way to show it is to say that any vector bundle has a complement such that the sum of the two bundles is a trivial vector bundle, and trivial vector bundles are in free objects, and being a direct sum in a free object is one of the definitions of projectivity, which you can carry out on the right-hand side. So projected C infinity modules, and well, vector bundles, at least the ones I'm talking about here, they are finite dimensional. So finite set of generators. So this one will be finitely generated. It's a direct sum in a finite dimensional free module. Okay, this is in fact an equivalence of the biggies. So for any C infinity M module, M, you can find some E such that those are isomorphic. And actually, this works nicely with morphisms. So if you have a morphism between modules, it comes from a morphism of vector bundles, etc. So those two notions are you can really replace one of the with the other when you work. So equivalence of predictors. Okay, so there are. I don't want to talk about connected spaces, so I'll have to do two little modifications. The first one is so. If I allow disconnected manifolds, I could in principle have vector bundles that have different dimensions over different connected components of the manifold. And these dimensions need not even be bounded. So I could over here have one dimensional, over here two dimensional, and so on. So so finitely generated will not really work nicely. What one can do instead is talk about locally finitely generated. So locally finitely generated modules over C infinity M is something where I can go frame, so without compactness, without connectivity, without connectivity. Okay. So locally, if you want to define locally finitely generated, the most canonical way to do it is every module you can sheafify, so turn into a sheaf by taking the tensor product over with the functions over a small open subset. You're kind of cutting away everything outside the subset, and you can ask, well, for every point there is a neighborhood such that the resulting module will be finitely generated. That's one way to do it. Maybe I'll write it out. For any P and M, there exists UP such that C infinity U tensor over C infinity M with the original module is finitely generated. And I should use the same R formula. So the moment where we are leaving the globally finitely generated setting, we are running into a different problem, and that's the fact that you can have very different modules which all locally look alike, and we would like to kind of the section functor will not describe all of them. It's exactly the difference between all sections of the vector bundle and compactly supported sections, and a lot of different things in between. So in order to compensate for that, I'll add the adjective global, and global just means that if I do this sheaf localization construction, and then I go back to the global sections, then I end up with the original module. In general, the result could be bigger, for example, and I don't want that to happen. So there is a canonical map between sheafification and then global sections and the original thing, and I want this map to be an isomorphism. And so by adding those adjectives, which are kind of compensating for, I would say, not very important problems, we get again an equivalence for general manifolds. Okay.
So these locally global locally finite generated modules, are they related to sheaves of locally sheaves of finite generated modules?
Yeah, that would be an equivalent reformulation of it.
Okay.
Sheaves, yeah, like a finite type sheaf of modules, basically, yes.
Finite type just means it's finite.
Yeah, locally finitely generated in a slightly stronger sense. Weird things happen over general rings over C infinity M. A bunch of notions which wouldn't be quite equivalent in general are equivalent because you have partitions of unity which allow you to do certain things.
Have to be projected.
Oh, sorry. Project. Sorry. That will be exactly the point to reach. So,
So you're still reformulating the classical.
yeah. Sorry. And to your questions, those are sheets of projective models that was holding it. Okay. And now I will write down somehow our version, our generalization of the theorem. So we start with, again, Anderson's manifold. The Tepui fibrations, which are vector bundles. I can again send them to C infinity of f by the section factor. So V over M is sent to gamma of V. Because of properties of C infinity M, the result will be again global. So not C infinity M, and now at the global, because that will certainly be the case. Now, two things one can prove. The first one is that this is locally finitely generated. This is a consequence of the fact in the definition that we have those cards or those plots, which are of which the space is locally in motion, together with the general properties of vector bundles and how to compute with them. One can actually show that locally any VB Tepui vector bundle Tepui is of this type V divided by RW. So vector bundle divided by image of a different vector bundle. So so one has the locally finitely generated property. The second property which I have to add is something which which one should probably call hybrid determinant. And this property means that in this module, because of the structure of C infinity M, there is a well-defined notion of what it is to evaluate a section at a module element at a point. And fiber determinant means that if a section is 0 at all points, then the section is also 0 in general. So, so the module R is fiber determinant if the map from R to the direct product for all points in M of R divided by the ideal generated by the functions vanishing at M in R. So if this map is injected. So let's recall IM is the smooth functions on the manifold which vanish at the point M. One should think of R divided by IMR as the fiber of R at M for a vector bundle that would exactly reproduce the fibers of the vector bundles. And we say that I want if the section has 0 value here, so it vanishes at all points, I want it to already be 0. So this is certainly something which will be satisfied by things which are constructed as sections of something. I should say, so the name fiber determinant is from Joel de la Toro, who wrote on similar subjects. The original reference is, I think, Jack Nestruyev, observability and principal and smooth manifolds, or something like that. But there it's called geometric modules. But the name is a little bit confusing, so we take the latter name. Okay.
Smooth is ghostless.
Yes. Ghostless. Oh, that's nice. Maybe we'll change notations once again. Okay, so global, locally finitely generated, and fiber determinant. And so theory, this is enough. So that's what theory. And the reason why we care is the module that we have in the very beginning, the compact, so the singular foliations. If you now really just take its global section, so you don't take compact support conditions, it is a module with all those conditions. So there is a VB Tepui such that the sections realize the singular foliation. So application. F. I'll put a hat on it because we have defined it as compactly supported sections. Now we take all sections can be realized as gamma of V. I call that A in this context because it's not just a vector bundle, it's actually an algebroid in those cases. So F has a bracket and it naturally transfers to gamma of A. F has a natural map to vector fields that naturally transforms into a map from A to Tm. So one should think of this A as a vector bundle, which kind of singular vector bundle, which is realizing the singular polygon. So nice aspects of this are, first of all, this type of singularity, which Tepui fibrations have. We actually came to it because we were studying the holonomy points of the singular foliation. So basically, this construction of Androlidakis and Skandalis on holonomy points, which we are kind of trying to reframe in this slightly more general setting, can be seen as usual Lie integration in the Tepui bundles over M category. That's kind of what we are working on now. Another advantage is that some constructions on foliations are a little bit strange. For example, time-dependent vector fields in the singular foliations have to be defined in a slightly weird way, because if you don't, you could again run into the flow of such a field does not preserve Lewis or something like that. However, if you define a time-dependent vector field in the foliation as a smooth curve going into A, then you are, or into gamma of A, then you are absolutely fine. And additional advantages from this perspective, it becomes relatively clear that a singular foliation is a Frichet space, even if as a submodule of the vector fields, it's not a closed subspace. So it kind of gives a different topology on this singular foliation, which turns it into a Frichet, or if you prefer compact supports, a left space. So you have slightly nicer functional analytic properties. And I think I was talking. Thank you very much for your attention. Please ask me about myself.
Please don't ask.
Oh, sorry. Please don't ask.
Question. So, one of the sources of these like singular foliation are loss structures, right?
Yes.
Can you say something about corresponding Tepui vector bundle of loss structure?
Well, it would be a quotient of the potential bundle, where basically, you're kind of dividing out the direction where the fibromized symplectic structure doesn't have directions. And so far, I don't really. Yes, I don't really have like a theorem or statement about them. So those certainly fall into this category. You can kind of take T star and look at the singular versions. One thing which Alfonso suggested, which we'll kind of look at when we have the differentiation integration, is one could in principle imagine to have something which is not integrable as a Poisson structure, but whose kind of version where you quotient out is still integrable in a slightly weaker sense. So that's kind of one of the applications that we hope to work on.
So I have a question about this fine-grained determinants. So what kind of examples does it exclude?
If you take the smooth functions on the line and divide out the ideal of functions that vanishing quadratic to that point, So this is R2.
Yeah.
It's like the first jet of a function. And if you calculate the fiber determination, it will kind of, sorry, if you calculate the fibers, it will just be trivial everywhere except at the origin. And at the origin, you will have R. So kind of, you can have the section X, which is non-zero here, but would be zero.
So because of nilpotent elements.
Exactly. Yes.
But is this not the so I2 or I squared is the image of a vector bundle map,
Mhm.
right? The small one, and C infinity is space of sections of the trivial bundle, right? One rank one bundle over R. So you're taking this quotient, isn't it the kind of module that you were including at some point?
So let me think. What you're suggesting is I take R2 over R,
Yeah,
another R2
yeah.
over R.
And the image of the map up top will be this I squared.
So you'll have to carefully distinguish. So when I say quotient, the
Yeah.
quotient is taken in a set theoretic sense. So it was it was E divided by R of F.
Yeah.
So this R of F, it's really the subspace. So you wouldn't see the difference between.
Spaces of section.
Yes, well, this is not the same thing. So basically, the gamma of this is not the same thing as gamma E
Yeah.
divided by R star of gamma. And despite everything you tried, I still say something about tensor product. So because it kind of has in here nicely, this is exactly the type of thing which can happen with tensor products. So if you take two modules and take their tensor product or even their completed tensor product, it will not in general be fiber determined anymore if you start with fiber determined modules. So this function cannot be monoidal because the tensor product of Tepui works absolutely without problems, but the result will be fiber determined. So basically what you would get is the fiber determination, so quotienting out the kernel of this, of the usual or of the completed tensor product. And kind of in some situations you might want to guard the usual one, in some situations you might want to have the fiber determined version.
I would also like to ask maybe about, since you mentioned pullbacks of the Tepui fibrations, maybe do you know how pullbacks along to homotopic or at least smoothly homotopic maps? What is the relation between these two pullbacks?
Well, you can pull back the whole smooth homotopy. So kind of the, but yes, but I'm not sure, like if I don't have in mind anything stronger than just the fact that smooth homotopies you can kind of just pull back with it, and so whatever structure would be preserved by having this parametrized version moving from one Tepui fibration to the other, you would have, because the smooth homotopies are parameterized by intervals, so it's kind of falling into the framework of allowed base spaces.
So you have like a isomorphism of the two Tepui fiber bundles.
I don't think they would be isomorphic. Like at least that's my first intuition. So take, no, I feel like so basically you can just take our example from the very beginning and take as the homotopy just something which moves from a usual point to the singular point, and kind of see this as a family over over the interval. And on one end you have trivial bundle, on the other one you have R. So kind of this. So it's kind of not creating isomorphism or equivalence.
But can you have some kind of local description where you have transition functions and stuff? Like
check homology. If it makes sense.
I don't know. I don't have any understanding of it because somehow the kind of the pseudo group in which the cocycles would have values is like really, really wild somehow here because you have kind of different dimensions, or like even without the dimension jumps, you have those weird non-Hausdorff versions. So yeah, I wouldn't know. I think there is this notion of DN spaces by Lossig, which I learned about 2 weeks ago in Reddit's Pralove, which I think this is the version where instead of the site of Euclidean spaces, you take this space of kind of fixed dimension and local diffeomorphisms between them. And there you have, I think, kind of a more reasonable check theory, but this is something which really models rather fixed dimension phenomena, like, for example, the quotient space bioregular foliations like that.
Also, you look at the classifying space.
I would not even dare to hope. Yeah.
If there are no further questions, then let's
I
end.
don't know, so can you do more differential geometry?
Sorry?
Can you do more differential kind of geometry connection and stuff?
Not on, so on those spaces, I think to a certain extent, yes, but it is very difficult. So if you want to kind of have proper differential geometry, there are multiple things you can do. In general, things like differential forms work well. Things like tangent vectors, vector fields work less well because it's like extending a contravariant functor or not quite a contravariant functor on this side perspective on it. So differential forms things work quite well. Tangent spaces, there is work by Christian Blomer on the tangent functor, which basically tries to establish under which criteria is there a reasonable notion of tangent space for diffeological spaces, and it's called elastic diffeological spaces. I think the preprint is out, but basically the idea is to kind of establish a list of criteria which you need to have a full Cartan calculus.
If you use geometric concepts on street, you can go to jets. So just using street.
Yes, so like in the vector bundle setting, yes. Sorry, I was not thinking like general fibrations, which are not all locally like those, as we have seen with this double cone example.
Thank you very much.